How to visualize multi-qubit states, no analogies. Imagine trying to see the full picture of a multi-qubit system in your mind. It's not like looking at a simple object. Instead, we work with vast mathematical spaces that grow exponentially with each added qubit. Visualizing these states helps us understand how quantum information is stored and manipulated. But how do we do that without relying on familiar analogies? Let's explore some methods used in quantum information theory. First, think about a single qubit. It can be represented on a Bloch sphere, which is a three-dimensional sphere. The state of this one qubit is described by a two-component complex vector, with the sphere showing the amplitude and phase. This visualization captures all the information about the qubit state. However, when we add more qubits, the state space becomes much larger. For 2 qubits, the space is 4-dimensional, and for 3, it's 8-dimensional. This makes the Bloch sphere impossible to extend directly. Instead, scientists use different tools to visualize multi-qubit states. One popular method is called the QSphere. It maps each basis state's amplitude and phase onto a sphere. The size of each dot on the sphere indicates how likely that state is, and the color shows the phase. This gives a clear picture of the entire state but can get cluttered as more qubits are added. Another approach is the statogram. It combines probability amplitudes and phase information into a two-dimensional diagram, making it easier to see complex states for larger systems. This method scales better and helps visualize states in quantum algorithms. There's also the dimensional circle notation. It maps the quantum state into a multi-dimensional space, highlighting properties like entanglement and whether the qubits are separable or linked together. This approach helps connect the math with visual patterns, especially for small systems. Additionally, the Bloch sphere binary trees organize multi-qubit states into hierarchical structures. These trees help understand how states evolve and how entanglement spreads during quantum operations. When working with these visualizations, it's important to remember their purpose. They help analyze quantum algorithms, debug circuits, and teach concepts. For example, visualizing the state during a quantum algorithm like the Deutsch-Jozsa can show how superposition and interference work across multiple qubits. Many tools, like Qiskit, include functions to generate these visualizations automatically, making it easier to explore complex quantum states. In essence, visualizing multi-qubit states involves moving beyond the simple Bloch sphere. It uses higher dimensional and abstract representations that encode the full complexity of quantum information. Techniques like the QSphere, statogram, and dimensional circle notation provide ways to see the structure, entanglement, and probabilities within these states. These tools are essential for understanding how quantum systems process information and for developing new quantum technologies.